So this is the data that we recovered from last week when you guys were simulating rolling a six-sided die over and over and over, and you rolled it 10 times and you wrote down the proportion of sixes that came up. And so as all of you did that, your data was compiled here in this little bar diagram. So just to summarize what we're looking at, it looks like of the 350 simulations that were run between all of us, there were 60 of those simulations where no sixes occurred in all 10 rolls. There were 100 where there was 1 6 out of the 10. There were another 100 where there were 2 6s out of the 10. 65 of the simulations had 3 6s out of 10 dice. 16 simulations had 4, 8 had 5, and one person had one simulation where 6 of the 10 dice were actually 6s. So that's very rare, but this did happen one time to one of you, and I don't necessarily know who it was, but that's pretty interesting. So what we're going to do is determine what the range of plausible values is based on this experiment, and what we're going to be using this for is just let's say that you're playing a game now with your friends that requires rolling 10 dice. And you all roll 10 dice and you're playing the game, and then one of your friends out of nowhere gets 6 6s on their dice. This simulation here, this study that we're looking at, allows you to determine whether or not that's a valid roll or whether there's a reason to be suspicious about that. Because we all know in the real world there is such a thing as foul play, right? So this is what we're trying to identify here. Maybe the dice are weighted, or maybe he didn't really roll them, he just dropped them, right? Something's going on there maybe. So when we determine the range of plausible values, what we're doing is looking at the middle 95%. So normally what that means is we make our little bell curve, and the mean goes in the middle, and we've got 1, 2, 3 standard deviations in either direction, and it looks something like this, right? But the middle 95% would occur between -2 standard deviations and +2 standard deviations. So if we do that, in this case, we would put our mean right here, and that's 0.173, that's the mean, and that comes from this information. And then we would add to that 0.123 2 times. Okay, so 0.173 plus 0.123 plus 0.123 is 0.419. And I could do the opposite as well. I could take the 0.173 and subtract 0.123 twice. So obviously this number is sort of interesting because it's impossible to get a negative number of sixes, right? That's not possible to do. So when we're thinking about in the reality here, in a realistic experiment, this can't be done. So we're sort of saying that we're willing to accept any results that are less than 0.419 if we were just looking at normally distributed data. Now we don't necessarily know if this data is normally distributed. So we're going to do our own little version of this. This is what we would do if the data is normally distributed, but since we're not sure about our data, we're just going to still take the middle 95% of the actual data that we see here. So what does that mean? Well, if we have 350 simulations, that means I have to take 95% of 350. Okay, so I'm going to multiply 0.95 by 350, and that gives me 332.5, which I will round up to 333. So what this means is I'm going to take the middle 333 pieces of information. So I'm going to throw out 17 data points, because remember, we have 350 data points, and I'm only taking the middle 333. So there are 17 data points here that I'm going to throw out. And the 17 that I'm going to choose are the 17 that are furthest away from the mean. So if I take a look at where this mean is, that's at 0.173, that would be about here, right? Let's say that's our mean. Obviously, 0.1 and 0.2 are not going to get thrown out. They're very close to the mean. Okay, and if I go out one more from there, I've got 0.3, there's a lot of those pretty close to the mean, and I've got 0, a lot of those are pretty close to the mean. But if I venture further away from there, I want to keep going outside of those until I've found the furthest 17 data points. So I would say that this 1 is one of the furthest data points, right? Because if I'm just looking at the way that this x-axis is set up, it is 1, 2, 3, 4, 5 decimal places away from where our mean would be. So I'm going to throw that 1 out. Now I still have 16 to go. I can throw out these 8. All of those can get tossed. So I've thrown 9 of them away. I still have to throw out a total of 17 though, so I do need to get rid of 8 more here. And I'll throw 8 of those away. All right, so if I throw away the 17 data points that are furthest from the mean, that's essentially me drawing a line and saying, I'm going to keep all of the data that's in here. And I'm going to say that this data is within the range of plausible values, meaning if someone does this on one trial, if someone rolls a 6 or rolls 10 die and gets 4, because there are some here that I would accept, 4 6s, I'm going to believe that. That's within the range of plausible values. However, if somebody goes out there and needs 1 roll to win the game, and they come up with 6 6s, I'm going to be suspicious, because that's not within our range of plausible values, and it's not something I would be willing to design a whole experiment around. So this is the amount of data that I would accept. Now, if we ran this experiment another 350 times, we may find that we have some different results. That's why I'm not willing to say that my data is normally distributed. If we're dealing with actual data, we can't say that it's normally distributed, so this is how we need to determine the range of plausible values. And so this is what you're going to do now for the activities that we participated in last week. I'm going to bring that data back, and I'm going to ask you to determine whether or not your data point is within the range of plausible values for that piece of information.